Hi guys, BuildZoid here, and today we're going to be taking a look at the voltage regulation and LLC settings of the MSI Z690 Torpedo EKX. Now, this motherboard shares its VRM design with the MSI Z690 Tomahawk, as well as the MSI Z690 Torpedo. So that's the boards that this basically covers, assuming that MSI doesn't make any major changes to how the BIOS sets up the voltage controller for the VRM. All of these boards use a monolithic power systems based VRM, as in monolithic power systems voltage controller, along with monolithic power systems power stages, which I'm pretty excited to be testing because you don't really see their parts on motherboards very often. They're normally reserved for like high-end NVIDIA GPUs. So yeah, kind of interested to see how they perform. And the oscilloscope is hooked up to the back of the CPU socket, which means we're going to see more overshoot in our measurements than what the CPU is experiencing. We're going to see less undershoot than the CPU is experiencing. And also our average voltage measurement is going to be higher than what the actual average voltage at the CPU is. And that's basically it. And the reason why we have all of those issues is because by measuring on the back of the motherboard, we're measuring before the impedance of the CPU socket, and the voltage regulator is regulating the voltage against the CPU itself, because Intel provides a connection directly, like a voltage measurement connection that goes very, very close to the silicon. It might even go into the silicon. Basically Intel has a dedicated connection of like, this is what you use to, control your voltage regulator. So that is why, like, if you measure from the back of the CPU socket, you're going to see the voltage go up if you have very, very aggressive LLC. Though there are other reasons to not use very aggressive LLC, which we're about to see, because right now the motherboard is running Mode 1 LLC, which is the 0 V-droop setting for this motherboard, at 500 kilohertz switching frequency. The voltage regulation on this LLC setting sucks, regardless of the switching frequency, which is another very interesting thing about this motherboard. Is actually, this motherboard does give you VRM switching frequency settings, but you get the best voltage regulation at 500 kilohertz, interestingly enough. So like raising the switching frequency on this board actually makes the voltage regulation worse. So I'm assuming that the VRM was like tuned specifically, like the control loop of the VRM was specifically tuned for 500 kilohertz, and at any other switching frequency, it just gets steadily worse and worse and worse. But unfortunately, I'm too stupid to understand how control loops work, so we're not going to get into the details of that. And I'm entirely serious about that. Like, the math required to understand control loops goes right over my head. So, yeah. Anyway, that doesn't mean we can't observe the effects of fiddling with settings in the BIOS. So, that's what we're basically doing in this video. Anyway, let's run some Prime 95 and move the mouse around, because that's the worst case scenario transient that you can apply to basically any motherboard, because Prime 95 pulls a ridiculous amount of current, especially with the 12900K that I have here. And by moving the mouse around, you basically interrupt Prime 95's workload, and that causes horrible overshoot and then undershoot once Prime 95 resumes. So, yeah, here we go. So we're gonna just run a little bit of small FFTs. So as you can see, our average voltage has gone up, right? That's the thing that I was complaining about. So average voltage has gone up. Previously it was at 1.22 volts, but because we're measuring on the back of the CPU socket, it's gone up. Our minimums, actually I should reset the statistics at this point so that we actually get new measurements. So without moving the mouse around, we get, 1.2 volts minimums on average relative to 1.24 volts average voltage, with worst case scenario minimums of 1.15. And I think me like touching shaking the desk probably just moved the mouse, which is why the absolute minimums shot down. We also have a peak to peak measurement here, right? So this is like from the top of the waveform to the bottom of the waveform, and we also have the absolute maximum voltage. So this is our overshoot measurement. I'm not too concerned about that. Basically, in order for overshoot to damage the CPU, it would have to be insanely high. I think for 12th gen CPUs, we'd have to be looking at overshoot that's like north of 1.6 volts or something, which you're just not going to see in any... Well, I guess if you found a terrible enough motherboard, you might be able to get that, but on a decent motherboard, like under normal loading circumstances, that's just not going to happen. Even in this scenario, like the thing is, like Prime 95 is so incredibly hot that you shouldn't be running it at such a high voltage that you could actually have enough overshoot to hit 1.6 volts. Like there's just no way. So anyway, I'm just gonna reset the statistics and now let's move the mouse around and observe where our minimums bottom out. And actually, I should be moving it over the actual Prime 95 window, because moving it around the desktop doesn't really do much. But moving it over here, yeah. Basically, Windows processing user input makes the VRM very upset. Well, more like stalls Prime 95 out, and that makes the VRM very upset. So I'm actually going to trigger on one of these spikes so that we can take a look at what's going on. Set this to single. Actually, I'm gonna try trigger on one of the downward ones. I'm gonna go down here, zoom in a bit, zoom in a lot, and then... Well, that's terrible. These are all really bad. So the issue with these is I actually have no idea why there's so many rebounds, basically. Can I get one that, like, ends while on the screen? There we go. So that is a mouse input spike, because for comparison, this is what happens without moving the mouse, is just that. And that's just the Windows event timer. So you always get these interrupts in any workload that's running where Windows is just checking that, you know, nothing has stalled out on the system. Anyway, if we pull this down a bit, set it to single, I move the mouse around, and we get this horrible mess. And the start of this horrible mess is basically Prime 95 getting stopped. And also here we can see something also, you know, getting in the way of Prime 95 running. Here we have some kind of steady, relatively steady load. And then here, I think that's the processing of the mouse input that's going on over there. Though it is worth noting that this VRM with the LLC completely maxed out also just kind of, yeah, doesn't... Like, I'm not sure if the double, like... Oops, wrong mouse. So this right here is very clearly the load release overshoot because Prime 95 gets interrupted by the Windows interrupt. What I'm not entirely certain about is why we get two downward spikes. Because I would assume that, like, in this area, Windows is just kind of, like, doing its thing, and then this downwards fall before... Because here, this is the VRM, like, recovering up to Prime 95 load. So this is, like, Prime 95 resuming load. So this right here kind of makes me suspect that the VRM is overcompensating and, like, making the undershoot worse than it needs to be. But I'm not 100% certain about that. Because I don't actually know, like, I don't know what's actually going on with the current draw. I would assume that our current draw is looking something like, you know, 200 amps while running Prime 95. Then the Windows interrupt hits, so our current draw drops way down to, like, maybe I shouldn't draw the graph that far. Well, screw it. Also, I'm screwing that up. The alignment's not going to work out. Anyway, Windows does its interrupt thing, and then it ramps back up to 200 amps. Ramps back up to 200 amps. So, like, this makes sense that, you know, during the 200 amp ramp up, we get this, like, rebound thing. Actually, the rebound would happen afterwards, so it would look like this, basically. So, yeah, you'd have the slide down, then Windows does its thing, but, so I'm not sure why there's this downward spike, because I would expect it to basically level off for a bit and then go down like that, but we're not seeing that. We just see a double spike, which is kind of weird. Either way, it doesn't really concern us very much because you shouldn't be using Mode 1 LLC. Like, regardless of what's causing this double spike pattern, the voltage regulation with maxed out load line calibration is terrible. So, yeah, like we don't really have to worry about this because it doesn't happen on other LLC settings. Yeah. So, like, this is awful, right? We're going from an average voltage of 1.24 volts all the way down to 1.15 volts. So basically, our CPU is pulling it's pulling power based on how much, basically based on the average voltage, and the temperature of the CPU is basically more is based on the average voltage. But our actual overclock stability is tied to the minimum voltage. So this right here, this is terrible. Like we're running, 90 there's a 90 millivolt gap between our average voltage and our minimum voltage, which means the CPU is running way hotter than it has to relative to how stable it actually is, because the stability is terrible. It's going all the way down to 1.15 volts. And then, of course, we also have the overshoot, but that's not in a concerning voltage range whatsoever. We're only getting, 1.24 up to 1.33 in absolute worst case. That's 90 millivolts of overshoot. That's, if the CPU was at 1.4 volts, that would still be under 1.5. Also, if you were running the CPU in Prime 95 small FFTs with 1.4 volts, it would be completely uncoolable. So good luck with that. I think you'd actually kill the CPU from thermal damage rather than overshoot. So, yeah, that's kind of the thing. Is that's one of the main reasons I don't really pay attention to overshoot. Is unless your motherboard is incredibly bad, it is extremely unlikely that the overshoot is going to be so high that it actually is a reliability concern for the CPU. Anyway, let's restart and use some far more reasonable LLC settings. Okay. Also, you'll notice that I actually have the CPU clocked really low because I really don't want it crashing while doing these demonstrations. I have a different video where I think I demonstrated what happens if you... Actually, okay, so I tested this ahead of time, so I already know what the voltages are supposed to be. So we're going to be going up to 1.33 volts. And we're going to switch over to Mode 2 LLC. And Mode 2 actually on this motherboard does a very good job. It's not the best setting, Mode 3 has a little bit less undershoot, and Mode 4 registers on the oscilloscope as having the same undershoot as Mode 3, but I would suspect that might be just because we're measuring on the back of the socket. So Mode 4 might actually be better, but my measurement methodology isn't able to pick that up. Either way, Mode 3 Mode 3 does actually do a very, very good job, and I'll actually show that to you, but for now, we're going to take a look at Mode 2 because there's one thing that I want to demonstrate that is easier to demonstrate on Mode 2 than it is on Mode 3 and 4, which is that the 1000 kilohertz switching frequency, and actually just raising the switching frequency on this motherboard above 500 kilohertz is a terrible idea because it makes the voltage regulation worse. So obviously now our idle voltage is way higher because, that's just how LLC works. So we're going to open up Prime 95 and we're going to start small FFTs. I'm going to reset our statistics. And as you can see, our average voltage is still the same, right? We're still, previously we were averaging 1.24 volts. Now we're averaging 1.24 volts. Our maximum voltage is still basically the same, right? We have a max of 1.32 volts, which is actually below the voltage that we have set in the BIOS, right? We punched in 1.33 volts, so actually doing a very good job there. And if I move the mouse around, we do get, spikes, but we don't get horrendously low minimums, right? If we look at our minimum readings, it's bottoming out at 1.22 volts. That's only 20 millivolts below our average voltage. That's actually... that is really good. That is, yeah, that's very solid voltage regulation right there. So yeah, good job to the board on that. And this is, Mode 2 with 500 kilohertz switching frequency, and I guess we could zoom in on one of these spikes as well right now. I wonder if they also have that double... Yeah, so I don't think that's overcompensating. Because we're still sort of getting that 2 spike thing, but they're like both upwards. And where's my cursor? There it is. So that would be prime 95 stops. I'm not sure why that happens. Tries to return back to idle, load resumes, and then it sort of recovers like that. So there's like a little bit of undershoot on that, which we can see in our minimums, right? Like there's 1.22 volts over there. And it can be like, the thing is, once we go to mode 3, we're actually going to be getting minimums of 1.23, even like worst case scenario. Like it's just, yeah. So it's not possible for a motherboard to have the average and the minimum voltage be the same. I don't think it's possible. But yeah, like 10 millivolts difference between average and minimum, like that's as good as it gets with my measurement methodology here. So, yeah. Anyway, so we do still kind of have a. I feel like I should be able to explain why this happens, but I might be forgetting something. Either way, we don't have horrible amounts of undershoot anymore, and that's the part I care about. Like, basically, the CPU is now running a lot more, now the system's going to be a lot more stable. And yeah, when you move the mouse around, evidently, a lot of time is just, like, there's a lot of processing that happens when you move the mouse, apparently. So, that's kind of interesting, which is why it's such a messy pattern when you do that. Anyway, we're going to stop Prime 95 again. Almost grabbed the wrong keyboard. And we're just going to restart. And we're going to try maxing out the switching frequency, which is actually going to make the minimums worse. So keep in mind that, for an average voltage of 1.24 volts, we were getting minimums of 1.23 and 1.22. Like, absolute minimum was 1.22, and average minimum was 1.23. And that's actually going to get worse once we max out the switching frequency, which is, I mean, like, I don't see it as a problem, because, like, just use the setting that works best, and the voltage regulation at 500 kilohertz is very solid. Like, it's either, like, or the motherboard has, like, a crazy amount of impedance to the back of the board. That's the other option, is, like, we're not, like, either the board's doing a good job, or it somehow manages to block all of the undershoot from reaching the back of the socket where I'm taking the measurement. I don't think that's what's going on, because MSI does have some, filtering capacitors on the back of the board. But yeah, that is theoretically a possibility. I don't think that's what's going on. But, it's just worth keeping in mind. Anyway, let's zoom out on this. Back up to 5 milliseconds. And now we're at 1,000 kilohertz. We're going to run small FFTs again. And if I reset our statistics, right off the bat, you will actually notice, without me even moving the mouse intentionally, I might have nudged it by, like, moving my hand around on the same mouse pad. Our minimums are now 1.19 volts. And if I move the mouse around intentionally, yeah, like 1.18. So, yeah, if you have a Torpedo or a Tomahawk, don't max out the switching frequency, which is, like, I'm really surprised by that, because in my experience, most motherboards that I've tested that had switching frequency options didn't benefit from... Actually, no, I think that's wrong. I think there was some Gigabyte Z390 boards that I tested where they actually ran best on 300 kilohertz. Not 500. It wasn't this drastic. It was like a 10 millivolt difference or something. But I think I have seen this once, like, maybe encountered it before. It just wasn't as significant. But yeah, on this board, definitely don't max out the switching frequency, because this it's just way worse. Like, way worse. So, yeah, that's interesting. But the good news is, like, the thing is, running the VRM at a lower switching frequency reduces how much heat the VRM produces, and if you're also getting just, like, the best voltage regulation that the motherboard can deliver, that's a win in my opinion, right? Like, I don't really see the downsides to that. But it does mean I kind of need to sort of probably like reevaluate my like overclocks on this motherboard, because for a lot of them I was using 1,000 kilohertz switching frequency, and now it's like, nope, that was definitely not the optimum method of doing things. Admittedly, I was using a very, very droopy LLC, and the effect is much less. Like on mode 3, the difference between 1,000 kilohertz and 500 kilohertz is far less. And on mode 4 and 5, it's basically impossible to see it. But, yeah, honestly, like, I gotta say, I'm very surprised that maxing out the switching frequency on this board actually just makes the voltage regulation way, way worse. Because most motherboards, it basically does nothing. Also, the MSI Z690-A Pro board, there actually you do want to max out the switching frequency because it does improve the voltage regulation a bit. So yeah, that setting is like that is a really awkward setting in my opinion. The thing is, yeah, like it's awkward in the sense that like I don't know how you'd ever, well, you could test this. There is a test methodology that you can do. It's just very, very tedious to test for this kind of thing, because you basically have to dial in an overclock within like a couple like 10 millivolts or something of being unstable, and then you can flick between the two VR. Like actually, this would be easier to test than load line calibration. Like testing load line calibration really sucks. If you're going between like, you know, two sensible settings. If you go from a sensible setting like mode 3 to mode 1, that's actually super easy to demonstrate that mode 1 is terrible. I've done that on videos in the past with other motherboards. I'm not going to do it here because that will take forever. But yeah, for this, you could just go between. Basically, you would have to dial in an overclock on the 500 kilohertz setting to be within like 10 millivolts of being unstable. Switch over to the 1000 kilohertz setting, and it would just crash, right? Because like the difference between these two settings is 40 millivolts. On 500 kilohertz, we were getting minimums of 1.22. On 1000 kilohertz, we're getting minimums of 1.18. So if you have an overclock that is within 10 millivolts of not being stable, and then you switch it over to 1,000 kilohertz, and then you run Prime 95 and you move the mouse, like, it's just going to crash instantly. Or at least it should. So that would actually not be that difficult to figure out, but it would be annoying. Like, it's an annoying thing to test, right? Like, nobody expects the higher switching frequency to make the voltage regulation worse. You expect it to make the VRM run hotter, but you don't expect it to make the voltage regulation significantly worse like that. Anyway, here goes mode 3 with 1.36 volts. And this is... yeah, and on mode 3, the board just does such a good job. Like, if I move the mouse around the minimums, they don't go any lower. Like, yeah, it just doesn't get worse. Our average voltage is still the same, right? We're still on a 1.24 average. Our overshoot, I think, is a little bit higher than on some of the previous tests, but again, nothing dangerous, nothing worth being worried about. And our minimums are like I can't measure better minimums than this, right? Like within my measurement capabilities, like this is as good as it gets. So yeah, like I gotta say, I'm kind of surprised that, you know, at mode 3, like this is like this VRM is found on like relatively budget Z690 motherboards. And so yeah, like I'm impressed. I'm very impressed. And also let's zoom in on one of these spikes just to see if I get any better at explaining them. No, they just look like that. Cool. Okay, so they just look like that, and I'm too stupid to explain why. Like the first upward spike, that one makes perfect sense. The second one, I want to say it's going back to idle or something, but I'm not entirely sure about that. Like, if I had a way to measure the current draw or the output current of the VRM, or more like, yeah, the current somehow, yeah, measure the output current of the VRM at the 5 microseconds scale. That like what we're seeing on the oscilloscope right now would actually be would potentially be very easy to explain. But I don't have a current measurement with that resolution. I have no idea how you would even try to measure that, though. I guess you could just look at the inductor current of a couple of phases. And there is equipment that can do that. It's very, very expensive. Anyway, let's zoom back out. So yeah, Mode 3 LLC does an excellent job. And you don't even need to have, like, it's not even crazy droopy, right? Like, we're at 1.36 volts and we're dipping down to 1.22. And the reason I say 1.22 is because for a given average socket voltage, the CPU voltage is going to be the same. So if mode 1, 1.22 volts, gives us an average voltage of 1.24, then mode 3, which is giving us a average voltage of 1.24, is also giving us 1.22 volts at the actual silicon itself. So, yeah, anyway, we're just going to stop Prime 95 again and try mode 4. And the thing with mode 4 is there's just not going to be an improvement anymore. Maybe if, I was taking the measurement closer to the actual silicon, we could see a difference, but from the back of the board, yeah, no. So, like, based on what I'm seeing here, mode 3 should actually be plenty good for, overclocking on this board. But, like, if you have the headroom, I would just use mode 4 instead. Right? Like, if you don't need, like, if your idle voltage isn't crazy high, and by crazy high, I mean north of, like, 1.45 volts, which also this board seems to have, like, some kind of slight negative voltage offset on the higher LLC settings, or droopier LLC settings, I should say. That makes more sense. Like, the annoying thing with manufacturers labeling their LLC settings, like, MSI has mode 1 as the least amount of droop. For comparison, like Asus, their least droop setting is level 8, or like, well, whatever is highest, right? So, yeah. Naming conventions, man. Anyway, let's run Prime 95 again. Did I forget to change the voltage? I did forget to change the voltage, didn't I? Well, I guess we'll find out. Yup, I forgot to change the voltage. We're down at 1.21 volts. Oh well. Shut down, restart. So we got to give it like, should it be like 30 millivolts extra? Let me just check my notes. Where are my notes at? Yeah, it should be 1.39. Called it. Cool. So there we go. Yeah. So like, I'd be perfectly comfortable like using 1.39 with mode 4 for 24/7. Nope, that's the wrong mouse. There we go. Because, like, the thing is, this board, right, like, we're idling right now, and we're only measuring 1.36 volts on the oscilloscope. And the thing is, like, you can even see that in the operating system. And I really don't, I don't think the CPU's, like, this OS might, actually, this OS is the OS with the screwed up idle. So, actually, we might just be pulling enough current that it's actually drooping on purpose. Not sure. I mean, we're at 20 degrees, so I don't think that's the case. Reporting 35 watts of power draw. Well, okay, I guess that might explain it. And our V-core is at 1.36 volts. Yeah. So, yeah, the idle's not great. So that might be part of that. Either way, like, I wouldn't be too worried about this. Anyway, let's run Prime 95 again. I'm just going to close hardware info. We're just going to run small FFTs. And now we're getting an average voltage of 1.24. And the minimums are 1.23 volts because it's literally impossible for me to measure anything better than that. Yeah. So, like, with this test setup, mode 4 and mode 3 perform the same. Though, again, if I think if I had a measurement that was closer to the actual silicon, we would maybe get a result that favors mode 4 rather than mode 3. Anyway, the other thing I figured I'd show you is... Actually, do I want to show it with... let's do it with Prime 95. So, small FFTs is a very sort of sustained load, because the CPU doesn't really... we're going to go to 256 and 256. Yeah, so small FFTs is a very sustained load, which is why, unless you move the mouse, you don't get a whole bunch of spikiness other than the Windows event timer. Because that workload actually fits entirely in like the L3 cache of the CPU, and so it never has to wait for memory access. Now, if you have a workload that's a bit more memory intensive, because it doesn't just fit into the L3 cache of the CPU, and that didn't work out. Oh boy. Still too small. Okay. I actually don't know what the next size up is. 320? 20? Is it running 320 FFT size? I'm not... Okay, 320 is a valid size. Okay, that's annoying. So we're going to have to switch over to 512 then? At some point, it should just devolve into a horrible mess. That's more like it. Yeah. The thing is, because the actual, like, average current draw is getting lower and lower, right? Sure, the sort of main body of the waveform, like this part is now, like, fatter. But the thing is, we're pulling less current. So the actual, like, worst case scenario spikes are actually relative to the sort of average voltage less bad, because there's just less current that needs to be stopped and started in a very short, period of short period of time. Anyway, if you keep cranking up the FFT size, eventually we shouldn't even be able to see the Windows event timer in it. I might just start large FFTs. Also, I can't see anything with this waveform on the screen right now. Let's get this out of the way. Yeah, like large... There we go, large FFTs. And you can almost not tell where the Windows event timer is now. Because this is, like, very, very memory intensive, but consequently the voltage is also... like, our average voltage has just kept going up as, like, increase the FFT size. Because the current draw is lower. So, yeah. Anyway, that's all I wanted to cover in this video. And somehow it's still 33 minutes long. Good job, me. So yeah, if you have one of these MSI Z690 boards that uses the monolithic power systems voltage regulator, mode 3 or mode 4 with 500 kilohertz switching frequency is probably like the best settings you can use for static voltages. Probably even for dynamic voltages, but yeah. Like, well, the 1000 kilohertz setting evidently causes some kind of issue, so I wouldn't use that at all. In fact, I wouldn't use... Like, I also tested 750 kilohertz before making this video, and 750 is also terrible. So, honestly, I would just leave it at 500 kilohertz. And then, other than that, for the actual V-droop amount, 3, 4, and, like, 3 and 4 is probably as droopy as you need to go. Because, yeah, the results are good. And then you have, like, 6, like, you have 5, 6, 7, 8, but, like, I wouldn't... Like, I don't see any reason to use, like, 6, 7, or 8. I really don't. Like, maybe mode 5 might be slightly better than mode 4 and 3, but, Like or I already can't measure a difference between mode 4 and 3, so I kind of doubt it. Yeah. Anyway, that's it for the video. So thank you for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. If you'd like to support what I do here with actually hardcore overclocking, I have a Patreon. There is a link to that down in the description below. There's also the AHOC Teespring store where you can pick up shirts, stickers, hoodies, posters, you know, the usual YouTuber merch. And also, as of recently, I have a Bandcamp because I have a solo, like, industrial metal, like, solo project. You might want to check that out. If, yeah, and so there's a Bandcamp link. And yeah, so Teespring, Patreon, Bandcamp, any of those, you know, helps out immensely with running the channel. So it'd be much appreciated if you'd check them out. And that's it for the video. So thank you for watching and goodbye.